All right, so 6.2 is going to involve addition, subtraction, and estimation. And we're still within this idea of doing rational numbers, and rational numbers are also known as, what else did we call rational numbers last time? Whole numbers are rational, but they're more specific. No. Somebody said it. Fractions, right? Rational numbers are a ratio. They're fractions, and they're fractions that are a very specific type. They're fractions of integers. So that's where all the language is that you guys are running around with here, is that if you have a fraction and it can be expressed as an integer over an integer, that's a rational number. So in this section, we're going to talk about adding and subtracting fractions, right? That's what we're going to be looking at. All right, so start with addition of rational numbers with like denominators. All right, so we have a over b and c over b, like denominators, and they're rational numbers. And if we add them together, what you'll see happen is that we only add the numerators together and the denominator does not change. It's a good idea to think about that as to why, because what do you think a common misconception is that your students might do if they were trying to add these together? Add the top and add the bottom, and they might do that whether the bottoms are alike or not, but the fact that the denominators are alike actually gives us a really good justification to show why. So let me give you an example and show you a picture. I'll have to, no, I think I have space at the bottom that I don't need, so we'll just do down here. So let's say that we were adding the fractions together that were 1/5 and 2/5. So we know, according to the definition at the very top, the answer should be 3/5. But it sort of looks odd that the denominator didn't change. So one way to do that is with a picture. I'm going to do my very best. I don't know that I should have done this in fifths, but we're going to do my best to cut this thing into fifths. Okay, that's not too bad. It's not perfect. In fact, it's really not perfect. Let's try that one more time. It's really not perfect at all. Actually, it's pretty sorry. Is that 4? Yeah. That's not bad. It's better than the first time around. Okay, so we have a pie, and it's cut into 5 pieces because you really like pie. And the first thing you do is you eat 1/5 of the pie. And then the second thing you do is that you eat 2/5 of the pie because you're really hungry. I'm sure it's something healthy, some kind of healthy pie, right? And if you look at this, you very quickly should say that the answer's 3/5, not 3/10, right? So these kinds of pictures really help solidify why in the world this works. And if we have the justification that as long as we have like denominators, we only add the numerators, there's no adding of the denominators involved, it makes it easier to justify the rest of everything that we're going to do later too. So this is an example of what's going on. Now, on Theorem 6.7, we actually have different denominators, right? And there's a couple of ways that we can handle things when we have different denominators. But the key to all of it is that the denominators have to be the same in order to combine them. Okay, that's true for addition and subtraction. It's not true for multiplication and division. But for addition and subtraction, we need the denominators the same. So there's a lot of different ideas of how to get denominators the same. In fact, 6.1 involved some of those, right? And I showed you several ways to compare fractions by getting the denominators the same. One of those ways was a least common denominator. And we said sometimes that's really easy to do. Sometimes we say, oh, look, one denominator's 3 and the other one's 12. All I need to do is multiply this one by 4. That's great. Sometimes it's not so easy to do. If you had 15 and 26, you might look at that and say, not so sure. Or even worse, 15 and 27. Well, they have some things in common, but not all of it's in common. One's not just a multiple of the other one, so now what? And so you can still get a common denominator without having to worry about it being the least common denominator. This definition that your book is giving is that kind of a definition. It's a way to deal with it without having to worry, is it the smallest common denominator that exists? So if you'll notice what's going on, and I'll do it a little bit bigger than what the screen's showing you. what they are doing is they are multiplying these two together, and then they're multiplying these two together, and then they're multiplying across the denominator. And that is equivalent to getting a common denominator. You might also recognize this is. You might also recognize that if you multiplied the first fraction by d over d and the second fraction by b over b, you'd get that same thing, right? The nice thing about the way that they're showing this is that there's a visual device to remember it, because you see these crosses, right? And you see this multiplication along the denominator. That's kind of nice. I've also had people draw this kind of an image before. I didn't learn this until one of you guys kind of told me. So they did this and made it look like a smiley face, which is clever. And so it's a visual picture of what's happening to make it easier for kids to remember. That's the idea. So this is one way to do it. Again, not the only way, but it is one way to do it. All right, so the first thing we're going to do is we're going to do two examples. First example is like denominators. So what happens when I have 1/3 and 5/3? I get 6/3, and you know better than to leave it like that. So what are you going to reduce it to? 2. That's right. Now the second one has unlike denominators, and I want to use the device that we just learned just for practice, and I'll make this a little larger so I can write a little more easily. So we're going to multiply across the first diagonal, and we're going to get 3. We're going to multiply across the second diagonal, and we're going to get 20. And then we're going to make a smiley face on the bottom and multiply, and we're going to get 12. And then we're going to reduce. 3 plus 20 is 23 over 12. And that does not reduce. And just like last time we talked about, unless you're told to put something in mixed numbers, or if the problem started in mixed numbers, there's no reason to become a mixed number. It's fine as is. So now we're going to talk about some mixed numbers. So mixed numbers are used in everyday life, represent values that are an integer combined with a proper fraction. Proper fraction simply means that the numerator is smaller than the denominator. And if the numerator is bigger, we call it a improper fraction. Yeah, so proper and improper. So for example, I ate 2½ cookies. 2½ is equivalent to 5 halves, but it would be very awkward to say I ate 5 halves cookies. We just don't talk like that, right? So that's kind of where you see the context used. These are very practical kinds of numbers. We use them all the time. So we need some practice on, or reminders on, how we go back and forth between the two kinds of numbers. Because in real life, it's easier to work with the improper fractions sometimes, and it's easier to work with mixed numbers sometimes. So going back and forth is a useful skill. So if you have 14 over 3, do you guys remember how you change that into a mixed number? Yeah, it's just division, right? I mean, that bar means division, so we actually just do division. We divide the numerator by the denominator. So how many times will 3 go into 14? 4 times, and we multiply 4 times 3, which is 12. 14 minus 12 is 2. Now, somewhere along the way, somebody told you, this is what my daughter's learning right now in 4th grade, that you write R2 and you say there's a remainder. And that's fine, except that doesn't put the mixed number all together, right? It's got all these pieces still, in different parts of the problem. So if you're wanting to write it as a mixed number, you write the whole number part. You take the remainder, 2, and write it over the original denominator, 3. So if you had 14/3 or 14/3 slices of pie, that would be equivalent to having 4 full pies and 2/3 of a pie as well. Okay. How about changing a improper fraction into a mixed number into an improper fraction? First of all, can I just ignore the negative? I can. It's just going to be part of my answer. It doesn't involve the process of changing anything. So the number I'm really working with really is 3 5/8. How do I change that into a improper fraction? Make a circle, or a half circle, right? So we can multiply 3 times 8. I'm going to show you why this works in a second. This is what you're remembering. What's 3 times 8? 24 plus the 5. 29, and this is equivalent to 29 over 8. And of course, it should be negative 29 over 8 because it was a negative number to start with. Here's what you're really doing when you do that. 5 over 8 was already there. What you're really doing is you're taking the number 3 and you're multiplying it by 8 so that you can write this as 24 over 8. 24 over 8 is equivalent to the 3, and you've got the 5 eighths. So now you've got 24 eighths and you've got 5 eighths, and you're adding them together. That's what you're really doing. You're just doing sort of a shortcut notation for doing that. Does that make sense? Okay. All right, the additive inverse property of rational numbers. Once we hit integers in Math 1, for those of you who've had Math 1, we added a property of numbers to our repertoire of properties. And this property that we added was this additive inverse property. And it said the following. It says if you have a number, and in this case the number is a over b, then there exists a rational number that is the negative, the opposite of that, such that when you add the two numbers together, you end up back at 0. And you guys know this is true, right? So what's the additive inverse of 5? Negative 5. And the reason is because when you add the two numbers together, you end up back at 0. I'm pretty sure those of you who are in Math 1 took a test that had a question like that on there. Okay, some of you did redos on it several times. Yes. But you know it now. So the same thing's true for fractions, rational numbers. They work the same way. So if I have a rational number 7/3, the additive inverse of 7/3 is negative 7/3. Yes. That's not a trick question, I promise. So negative 7/3. All right, we also have the addition property of equality, same property we had before when it was other types of numbers. And it says that if we have two numbers that are equal, right, in this case the a over b and the c over d. Now it seems sort of weird to say that because they don't look equal, but I mean, like, you know, 3 over 6 doesn't look equal to 1/2 either, right? But they are. So it's just two different expressions for the same number. That if you have a third number, e over f in this case, and you add that value to each of the original two values, they don't change. Okay, so I'm going to do it with whole numbers because the process is the same, but if you have 3 equals to 3, and you add 7 to each of them, 3 plus 7 is still equal to 3 plus 7. Okay, so it's perfectly fine to add a value as long as you add it to both sides or both values that were equivalent to start with. We use this extensively when we are working with solving equations, right? So that's where this sort of leads into. Now, most of you are not going to be working with kids solving equations. That's very end of some of the kids' experiences in elementary, the early part of junior high. But this is leading them into that idea. So that's what's going on here, and that's what we want to keep in mind, is that we are working towards something else that happens beyond your classroom. Okay. So we're going to use them in an equation sense to get a feel for how they work. We have two mixed numbers in this problem. So this says x minus 2 1/2 equals 3 1/3. Now there are two distinctly different ways to solve this problem, and I'm going to show you how to do both of those ways. Does anybody remember a way to solve this problem?
You could have 2.
Okay. So all right, so Angela has me looking at this value now. I've got 3 1/3 plus 2 1/2. Now, that's actually what we're going to do in either of the two cases. I mean, that's kind of the first step in either of the two cases. So my question is, how do I add 3 1/3 and 2 1/2 together? And this is where there's two different ways to do that. Thoughts? Okay, so you want to get a common denominator. So can you tell me what you're thinking, Kristen?
Change them into the actual fraction, not mixed fractions.
Okay.
And then...
That's what I wanted you to say. So this is the approach you're using. This is the improper fraction approach. So one way to do this problem is with improper fractions. So Kristen wants me to take 3 1/3, turn it to improper fractions. So what would that give me? 10 thirds. How about the 2 1/2? What would that give me? 5 halves. And then what? You can get a common denominator, and just for the sake of showing it one more time, I'm going to do the cool little visual. Yeah. But you don't have to. So this would be 20 plus 15 over 6. What's 20 plus 15? So 35 over 6. So here's a question for you. Do you get to leave it as 35 over 6? No. Lena's shaking her head before I even got the rest of the question on my mouth. Well, why not? I told you could leave things as improper fractions. What's the difference?
Mixed numbers.
This question started out with mixed numbers. And if it starts out with mixed numbers, your answer is going to be mixed numbers. So yeah, let's take a look at this then. I need to divide 35 divided by 6. So how many times will 6 go into 35? 5. 5 times 6 is 30 with the remainder of 5. So this is equivalent to the value 5 and 5/6. How many of you learned this way? Okay, that's the way I learned too. But this is not the only way to do the problem, and I want to show you the other option because there are cases when the other option is much friendlier. And to be very honest, I like it a lot better than what I learned, which is the one we just did. The other approach is to keep things in mixed numbers. Now, it starts out the same way. We move the 2 1/2, and you add the 2 1/2 to both sides. All of that's the same. So I get to the same point. This is the same. This is the same. I get to the point, I get to the point here where I have x equal 3 1/3 plus 2 1/2. Okay, that part's the same. The difference is we don't make them in proper fractions. Here's what we do instead. We add the whole number parts together, and then we're going to add the fractional parts together. What's 3 plus 2? 5. And then I can use that same cool imagery that I did on the other one. The benefit in this point is that the numbers are smaller. 2 plus 3 over 5. Over 6. So this is 5 and 5/6. Your fractions end up being smaller fractions. Your improper fractions you don't have improper fractions with larger numerators when you do it in that approach. That's really nice. And if you think about it, really, this is what you would do if you were working with physical objects, right? Kristen's got 3 1/3 cookies, and Lydia's got 2 1/2 cookies. We wouldn't divide all the cookies into sizes of 1/6 and then count the 6th up, would we? We wouldn't. We'd sort of group the whole cookies together and count them, and then we'd try and figure out what to do with the little pieces of the cookies and how much that is. So this one has a really nice imagery involved with that too. That said, on your homework, if it doesn't specify what to do, you can choose whatever you'd like, just as long as you're aware that I can ask you to do either way on the test. So just make sure you know both of them, okay? All right, subtraction. Subtraction is almost just like the addition stuff, but let's start with the definition first. The definition of subtraction says that if we have a rational number a over b and another one c over d, and we subtract them, we will get an answer. And it'll look something like an e over f. And that answer has the property that when I add that value to the smaller number, I end up with a larger one. And I'm just going to show you something again with whole numbers because it's easiest to see and not to have to work too hard to see what's going on. If you have 5 minus 2, you know it's 3. And one of the ways kids first learn that 5 minus 2 is 3 is they say something like this. They say, how many do I have to add to 2 to get 5? Well, it's 3. So the answer to 5 minus 2 is 3 because 2 plus 3 is 5. Right? You use prior knowledge. You build upon that when you're creating subtraction. There's no reason to start from scratch because it's not something that's new. It's really just a reiteration in a different way. All right, Theorem 610 says that if we have two rational numbers that we're subtracting, that it's equivalent to saying that they're added with one of them being negative. It's an addition of a negative. So if you're looking at the numbers, again, I'll use whole numbers, not because they have to be whole numbers, but that 5 minus 3 is the same as saying 5 plus negative 3. That's all Theorem 610 says. All right. This is the slide that's just a mirror image almost of the addition slide. So if we have like denominators and we are subtracting those two fractions, we simply subtract the numerators. And we could draw a picture with the pieces of the pie and do the exact same thing we had before. You know, we have 3/5 of the pie shaded in, and then we eat, 3/5 of it's left over from the party or whatever, and we eat 1/5 of it, so minus the 1/5, how many fifths are left? We could do that. And then if we have the different denominators, you can see that wonderful imagery that we had with that before too, where we have our smiley face going on. Okay, it's just the same thing with a different sign in the middle. Okay, so we're going to take a look at a problem with subtraction. Well, we might look at it in subtraction. We'll see. A fabric. So you may not like fabric as a very good example, and it may not be a good example for your students as you work forward with them. But what you'd like to do eventually is to use examples that do matter to your kids. And the more you can figure out about your kids, the more the examples that you create are going to actually make sense of why in the world would I ever want to subtract mixed numbers or whatever. Okay? So you're going to see me ask you questions at time. Again, many of you have already seen this happen. What I tell you to create something that happens, right? You say, you create a subtraction problem with mixed numbers that's both realistic and interesting to a 4th grader, or something like that. All right, so Martine bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yards, and a vest using 1 2/3 yards. How much fabric will be left over? What are we going to do? There's more than one option, so that's why I'm asking. What are we going to do? Okay, so what do we want to add? Somebody said add up something. Hannah wants to add. Hannah, I'm not making you add it. I'm just asking you, what would you like to add?
All of the yards and stuff she's going to make.
Okay, so you want to add these 3 together.
Yeah.
Okay, so Hannah says she'd like to do 1 7/8 plus 2 3/8 plus 1 2/3 first. And I'm just going to indicate that we're doing that first and put it in parentheses. Okay? Okay, once we find that number, whatever it is, then what are we going to do? All right, so we're going to subtract it away from the 8 3/4. So this is the result of what we're going to do. What else could we do instead of this? Well, this is an expression. We don't have an equation yet because there's no equal sign. We could subtract each one. And if you think about what she's actually doing in the fabric, that's actually how she'd process through this problem if she were really doing it. She'd lay all the fabric out, and she'd lay her skirt pattern down, and she'd cut it apart. And she'd lay her pants pattern down, and she'd cut it apart. And then she'd lay the vest pattern down, and she'd cut it apart. She'd actually do multiple subtractions from the physical fabric, right? And that's fine, too. Either of those approaches are perfectly fine. We've already got this one written down, so this one I'm going to go with. Okay? Sound good? However, you see mixed numbers with different denominators. There's addition involved, and then there's subtraction. And since you all seemed much more familiar with the improper fraction approach, I'm going to do the mixed number approach again on this one to show you how that would work. Okay? There is a nuance to it on this problem that you should be aware of with subtraction that occasionally will happen. All right, so first thing first, we collect inside the parentheses. My 8 3/4 is going to stay out. We'll deal with him in a minute. We're going to collect the whole number parts. So I have 1, 2, and 1, which is a total of 4. I have 4. And then I have 7/8 and 3/8. Well, that's kind of nice because I can combine those right away. What's 7/8 and 3/8? 10/8. Yes, it is 5/4. Do we want to write it as 5/4 right away? Okay.
Wait, don't you mean 3 plus 5/4? Because that's what I'm thinking.
3 plus 5/4. Oh, we're adding this one to it as well, Leah. This one, this 2, and this one. All of those to get the 4. Yeah, that's what we did first. You could do it like you're suggesting. It wouldn't be wrong. You just have to add one more time at the end. So we kind of did it all at once. And then I still have that 2/3, right? All right, so then I can make a smiley face. So this is 8 3/4 minus 4 and what? I'll start 15 and then where? 8 over bigger. 12. Yeah, 12. Okay, so I have 8 3/4 minus 4 and what? What's 15 plus 8? 23 twelfths. 23 twelfths looks a little weird because it's an improper fraction in the middle of doing all the mixed number stuff, right? It looks a little weird. So let's go ahead and change that too. So I've got 8 3/4 minus, and what I've really got is 4, and then this would be 1 11 twelfths, right? Is that, did I get that right? 11 twelfths. So back up here. So this would actually be 5 11 twelfths then, yeah? I turned 23 over 12 into a mixed number. I divided. What I did, to be honest, Gary, is I recognize that's just one short of being the number 2 anyway. So I have 11 left over of that. Yeah. And if you're not sure, if you were working with a child, you would want to show that step, right? I mean, you would show the division so that they can see where that's coming from. Now, we did addition before, and this is subtraction, so it is a little bit different. I still can subtract the whole number part, so it's 8 minus 5? 3. And then to this, I'm going to add the subtraction of the mixed, or the fractional parts, 3/4 minus 11 twelfths. Now, there is an innate problem with this. I'm going to get a common denominator and show you why there's an actual problem with this, and I'll do the common denominator the way you guys sort of wanted me to all the way along, and just multiply this by 3. What do you see is going to be a problem here? We actually have a negative, right? 9 twelfths minus 11 twelfths is going to give me a negative value. And that's a little bit odd. I'm going to go ahead and get that negative value, but then I'll just show you how we would deal with it with using this kind of an idea. So this would be 3 minus what? Well, I should say 3 plus what? Negative 2 twelfths, which is the same as negative 1/6. I'm going to go ahead and write the 1/6 for the moment. So really, this is 3 minus 1/6. Yeah? Which is, what was it? 2 5/6. And you might just recognize that. If you didn't, maybe it wasn't so clean, or it wasn't so just obvious, or you just don't like numbers of this variety. Another way to think about this is to change the 3 into a 2 and write a 6/6 and a 1/6. This 2 and this 6/6 is the number 3. Okay, 6 over 6 is 1. So you're breaking the number 3 apart into 2 plus 1. Okay? That's the tricky step. That's the part that's a little bit odd to recognize. You end up with 2 5/6 at the end. Can you do it with improper fractions? Sure you could. You could definitely do it with improper fractions. You will end up with quite large fractions, just so you know. I have this one written down, and I have fractions that look like 210 over 24, 45 over 24, 68 over 24, 40 over 24. I have big fractions written down. So, you know, there's a plus and a minus to both approaches. It's just an option. The other thing to be aware of is as I approach things or show you different approaches to things, is that you may not like them, but that doesn't mean that some student you're teaching might not like them better. And it may make more sense to them. So it's a really good idea to at least keep in the back of your mind the different techniques for doing something, because if you encounter a child who really, really does not like your improper fraction approach, even though it's your beloved favorite one, you need another option to show them what to do. And this would be an example of one. Okay? All right. A couple more slides and we're done for today. Just with new stuff. You guys get to have some fun in groups. But definition of less than and greater than. All right, so to start with, this looks, again, just like what we did with whole numbers. So if we have A over B is less than C over D, it must mean that the larger number C over D minus the smaller number A over B is positive. And you know that's true because it's like saying this. If 5 is less than 12, the only reason that happens is because 12 minus 5 is greater than 0. If you take the larger number and subtract the smaller one, you're still having a positive number left over. And we can flip this around and it works the same way. That's what the other part is down there. It's telling you that you can actually flip these fractions around. So if C over D is bigger than A over B, it means that A over B is less than C over D. Right? So if 5 is less than 12, it means 12 is greater than 5. Okay. Now there's an estimation portion of this section that's talking about convenient fractions. Convenient fractions are fractions that are roughly equal to what we're given but easier to work with. Now, you saw an example of that in the last lesson. There was an example, I can't remember, I think it was Kinsey who said there was a number that was like 51 over 210 or something, and you were like, well, I can just look at that and kind of say about what it is. I mean, that's kind of our approach and one of the approaches to thinking about that. Well, because roughly the top was 50 and roughly the bottom was 200, so it's about 1/4. That's the idea of convenient fractions. It's this idea of approximating to something that's just easier to work with when an approximation is sufficient. We don't need an exact answer. Why not make it something that's easy to work with? So some examples of convenient fractions are 1/2, 1/3, 1/4, 1/5, 2/3, 3/10. You can have 1/10. I mean, there's lots of different things that you could have. And as you're looking at these, the questions they're going to ask you are going to look like this. Estimate the following fractions. And they're going to ask you, is your estimate high or low? Now, in some of the problems, they'll actually say, estimate the fractions to be which of the 4 numbers it's closest to. Is this closest to 0? Is it closest to 1/2? Is it closest to 3/4? Or is it closest to 1? It's like they're going to it's almost like multiple choice. Okay? So you don't have to do a lot of calculations and wonder, is this the answer they're going for? It's one of 4 answers or something like that. Now, if they don't give you that, then you're trying to figure out what they maybe would be looking at. So what about 12 over 82? What could I estimate or change the 12 over 82 to be easier to work with? 10 over 80 would be much nicer because 10 over 80 reduces to what? 1/8. So I don't want the equal sign. This is an approximate. But the 10 over 80, that doesn't look like an 80, actually is 1/8. So this is approximately 1/8. We'll answer that high-low thing in a minute. How about 2 over 1001? Yeah, it's about 1 over 500. And again, if they were giving you multiple choice, 500, it's probably the answer 0. I mean, that's almost nothing, right? If you put it in your calculator, it's going to give you a very, very small number. It's nearly 0. But if you need an approximation that's actually still in fractional form, that 1 over 500 is reasonable. Yes?
On A, couldn't you do like 12 over 84?
You could.
And then that'd be 1/7 though, so.
That's okay.
It's okay.
Yeah, that's okay. It's a little bit less likely that you're going to go that route because not everybody's going to know multiplication tables of 12s. Or if you had had something like 14 on top, even less likely. But there's nothing wrong with it. If you see that and think, oh, it's about 1/7 because I see 12 over 84, that's fine. That works too. All right, let's answer the high-low question. Sometimes that's easy to answer. Sometimes it's not. So 12 over 82. Is that high? Let me say it this way. The 1 over 8 that we approximate to, is that number higher or lower than the one before?
Anyone considering dividing it by 2?
Well, we're looking at 1 over 8. I don't think we're going to divide 1 over 8 any further. It's as simple as it's going to get.
What about 12 over 82?
We already did that. We already took the 12 over 82 and we turned it into roughly 1/8.
What
Right.
about dividing dividing it by 2 to see if it's high or low.
I'm not sure how dividing that number by 2 is going to help us with the high or low question. There's a couple of things you can do. Did you have an idea, Angela? Oh, my screen went away. Okay, just a sec. All right, so one thing you can do if you're having trouble looking at them to make the decision, so you can grab your calculator, and what could you do with your calculator? Yeah, you could turn them both into decimals, you could divide, right? So you could actually figure out, I mean, hopefully you know approximately what 1/8 is. Do you? It's 0.125. It's half of a quarter. All right, 1/4 would be 25 cents. Half of a quarter, it's 12 and a half. So it's 0.125. If you didn't, you can use your calculator to do that. What is 12 over 82?
Approximately.
0.146. All right, so is our estimate, the 0.125, that 1/8, is it high or low? It's a low estimate. We got a value that we're using as an estimate that's lower than the actual value. Another thing you can do is you can compare what you're actually doing. Now on this one it's a little bit trickier. Let me actually use the example you gave, Kristen, and changing it to 1/7 to show you another way to think about it. So if we did what Kristen suggested, and instead on this one, I'll erase in a minute just so I have some more space, but if we left the 12 put and we changed the 82 to 84, so that we ended up with 1/7, do you know if 1/7 is a high or a low estimate? What is your calculator going to tell you? What does the calculator give you for a decimal? 0.142. It's really close, right? It's slightly lower. You know, one way to decide that it's lower or know that it's lower is because the numerator stayed the same, right? And the denominator got bigger. What happens when denominators get larger? Fractions get smaller, right? You take that pie, and 8 people show up at the party instead of 6. Everybody can still have a piece of pie. They just don't get as much pie as they were going to get. Yeah? Everything's now smaller. Same thing. So if you only are changing the numerator or the denominator by itself, nothing else is changing, it's pretty easy to see which one's higher or lower, and you don't really need a calculator to make the calculation. But if you change both numbers, that gets trickier. Now, on this one, we actually, the one before here, all right, we'll do it this way. On this one right here, what we actually did, or what you guys probably were actually thinking, is this is the same thing as 2/1,000, right? That's where the 1/500 came from. So in a very real way, we only are changing the denominator, and we're making the denominator what? Smaller, which makes the fraction larger. This is a high estimate. Now, it's not any too hugely high, but it's larger than the value we started with. Okay. I'm fine with you using your calculator to answer that question. I just want you to think about what you know about fractions, making things bigger or smaller. At least when just one thing's changed, you can make that answer without the calculator. All right. Here's your chance to look at somebody else and to make up a question. So I'm going to put you in groups in a minute anyway, so now's as good a time as any. I'm going to put you into groups, and then we're going to work this problem, then you're going to move into something different. Okay? All right, what did you guys come up with? Somebody tell me what your problem says. Yes. Heather? That's not right.
I mean, we can do 5 whole pies. You've had me already.
I know I've had you in class. This is so bad. Ashley. It starts with an Ash. That's awesome. All right, Ashley, what do you got?
It's Thanksgiving. We have 5 1/4 of the pumpkin pie. My family ate 2/3 of the pie. How much is left over for the next day?
Now you have to be careful. Be really careful how you word it. Did they eat 2/3 of the pie, or did they eat a 2 1/3 amount of pie? Do you guys hear the difference? No. You see, if you had 5 1/4 pies and you ate 2/3 of them, that's a multiplication problem. It'd be like sticking all the pie together and splitting it somehow into 3 equal portions and eating 2/3 of the portions of the 5 1/4. I'm really glad that you said the question that way, Ashley, because I have a lot of people who will write questions that'll do that. You have to be really careful about what you're clarifying this thing to be. So let's take what you said and let's reword it just a little bit so that it will work as people are erasing. Lots of people,
Yeah,
yeah.
I'm so confused.
Okay, so let's, it would be like saying this. Let me use whole numbers to show you why this could happen. Let's just say we had 5 pies. What you said is my family ate 2/3 of them.
Well, we had 5 1/4 of a pie.
Okay, but 5 1/4 of a pie would mean 5 whole pies and 1/4 more.
Okay.
That's what that would mean. I'm just using number 5 so I can draw a picture.
Okay.
Because if you had 5 pies and you ate 2/3 of them, it would mean you'd eat 1 pie, and then you'd need to eat 2, because that's not a good way of doing it. Let me do it this way. Terribly not at all accurate. And if you're going to eat 2/3 of them, then you would need to make sure that you ate 2 out of every 3 slices of those pies. So you eat this piece and this piece, this piece and this piece, this piece and this piece. This would be 2/3 of your 5 pies. It's not a subtraction problem actually, right? It's actually a multiplication problem or division depending on how you're looking at the problem. So I want to take your question and we'll just reword it slightly. And so instead of saying that we eat 2/3 of them, first of all, it's not 2/3, it was 2 1/3. So we can talk about it and we can say we have 5 1/4 of a pie. Like you said, you have 5 pies and 1/4 more, whatever. My family eats 2 1/3 pies. Not of a pie, but 2 1/3 pies. So that means we eat 2 whole pies and we eat 1/3 more of something. And then we can talk about how much pie is actually left over. So we can work with it, we just have to be really careful about the language we're using to describe it. Okay, so pies is a good way to do this. Kids like pie, right? Mm-hmm. Sure, why not? Okay, what else do we have besides pie?
We got
What do you got,
wood.
Leah? You got wood. Wood's a good example, right? Okay, what do you have for wood? Do you want to read it, Leah?
Okay, suppose we add 5 1/4 feet of wood. Of said wood, 2 1/3 feet has been cut off. How much wood do we have now?
Okay, so we've cut off a portion of the wood. This is kind of like our fabric example. And if you wanted to create more interest for your students, you could talk about what the wood's going to be used for, right? To make a birdhouse or something a kid would like to do. They'd make the pine wood derby car, whatever. Okay.
What about firewood?
Yeah, but I don't know that the kids are going to care very much about how much firewood it is. All right, one more example, real quick. What do you got?
We said pizza.
Pizza. Oh, pizza's a great example, right? Who doesn't like pizza? Well, actually, my sister didn't like it growing up, but most kids do. Yes, pizza would be a great example. So we could talk about it very much like you talked about the pies, right? Yeah. Okay, everybody good with that? And we understand the clarification on the word of. Keep in mind, too, the word of often means multiplication in mathematics. So if you're using of, be really careful how you're using it. All right.